All right, so for section 910, again, Taylor and Maclaurin series, we've already talked about Taylor and Maclaurin polynomials before in 9, I think 9.7 and 9.8. So now in 9.10, they're going to talk about the series portion of it. So there's a definition that they give us. Let me write this down for you guys. So definition of a Taylor and Maclaurin series. So it says if a function, so a given function, okay, so if a function f has derivatives of all orders at x equal to c, then the series and they give us the sum as n goes from 0 to infinity of f to the n of c, that's the nth derivative, divided by n factorial of x minus c to the n. If you guys remember this part right here, I'll erase what I'm about to do right now, but this part right here is what we learned in 9.7 and 9.8, right? The definition for the Taylor coefficients, right? And how to find those little pieces based on whichever derivative they wanted, and all that stuff. So, and then the x minus c tells you your center. So, so that part was already known. So they're just putting it in terms of a series now. And that would be equal to f of c, right? And this is stuff that we've already seen before. F prime of c, x minus c, etc. And then f to the nth derivative of c over n factorial x minus c to the nth, etc. So that is called a Taylor series. So this is called a Taylor series centered at C. As usual, they always talk about the Maclaurin one, so they'll say, moreover, if the center is at 0, then this series, as n goes from 0 to infinity of, what could I do? I guess I could do this. F to the nth derivative of 0 over n factorial x to the n is called the Maclaurin series. So it's called a Maclaurin series centered at 0. Now, if you remember how with power series, they would write like a sub n x to the n, right? So it was like a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus a sub 4x to the fourth, right? That's what they would write in the power series. They would use these a sub n terms. So I'm just going to let you guys see right here a note really quick. So a real quick note that a sub n for a power series, when you talk about Taylor and Maclaurin, is defined by this term. Okay, so this is your a sub n for a Taylor and Maclaurin. So if you're trying to find like the first term, second term, third term, etc., you know, your nth term, that's how you would figure it out. So they call them your coefficients. All right, so that's the main difference. Because remember, the stuff that we did before, just recently, looked like this. right? A sub n x to the n. So they're just saying, hey, a sub n is your f to the nth derivative of c over n factorial. Right? So they're just trying to say, like, check that out. There is kind of something that's similar between those two things. So let's do an example really quick. So example number 1, we're going to use a function f of x equal to sine of x to form the Maclaurin series. To form a Maclaurin series and determine its interval of convergence. Okay, so use a function f of x equal to sine of x to form a Maclaurin series and determine its interval of convergence. So they're saying, how can you write your sine of x function as a Maclaurin series? And then once you figure that out, where does it converge? Over what interval? Okay, now we've kind of done this before. And I'm not sure if you guys remember this, but we were able to, bless you, we were able to define sine of x before. You guys remember the way it starts? Remember, sine is an odd function. So you start with x to the first, then minus x to the third over 3 factorial, then plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus etc. Right? So they're saying, okay, since you know this, and notice it is centered at 0, right? It's Maclaurin. Since we know this, then can you write a series for this? Well, let's see. I know that this is alternating, okay? So we'll start from 0 to infinity. I know that it's alternating. So if I plug in a 0, that would be a positive 1, so good, okay? Now, I need to make sure that my first power is a 1, right? And my next power is a 3, and then the next one is a 5. So I need odd powers. That means that I could either use 2 to the n plus or minus 1. Those are odd powers. Which one should I use, the plus or the minus? So if I use a minus, plug in your 0, do you get a power of 1? No, I get negative 1. So then I should use the plus. 2n. Oh, it's because you're supposed to know that a power of 2n only results in even. Because I don't even know when you guys learned this, maybe in Algebra 1, they talk about, like, how can you write even and odd numbers? An even number is x times 2, always. Because 2, if you can divide by 2, it's always even, right? So if you multiply any number by 2, it's always even. Now, to create an odd number, just take an even number and either add 1 or subtract 1. Right? So 2n plus 1 is representative of odd numbers. 2n minus 1 is representative of odd numbers. But 2n is representative of even numbers. So since I only needed odd, then I said 2n plus 1 or minus 1. But we figured it was plus 1. And we're going to divide by what? By the same power, right? 2n plus 1. Because the first factorial needs to be a 1, the next one needs to be a 3, the next one has to be a 5, and then a 7. So here's my Maclaurin series for it.
Why do you have to put the negative 1?
Because it's alternating signs. Notice it's positive, negative, positive. Then I don't need it, yeah. If it was always plus, then I wouldn't need to do it. Or if it was always a negative, then I just put a negative 1 in the very front of the summation. Yeah. But this one's alternating, so I got to put it there. All right, so great. We have what they wanted. They said find a Maclaurin series. I just did. Okay? But then they say, all right, aside from that, we need to figure out where does this converge, right? What is its interval of convergence? So to figure out the interval of convergence, we were talking about how you could use many different tests, but the ratio test was always a good one, right? So let's try using the ratio test for this. So I'm just going to kind of put right here, ratio test. So it's the limit as n approaches infinity of, now since it is a fraction, I'm going to, instead of dividing by the fraction itself, I'm going to multiply by the reciprocal at the end. Okay, so remember the first thing is x to the 2 times n plus 1 over 2 times n plus 1 plus 1. Remember, you're always supposed to add 1 to the n value, right? So it should be n plus 1. It's a sub n plus 1 divided by a sub n. That's a definition. Times 2n plus 1 over x to the 2n plus 1. So let's clean this up a little bit. This is x to the 2n plus 3 over 2n plus 3 times 2n plus 1 over x to the 2n plus 1. Oh, you know what? I forgot to do something on the bottom. It's supposed to say factorial on the bottom, right? I forgot to write that down. So I'm gonna use a purple marker. In the Maclaurin series right here, this should say factorial. Because it's 1 factorial, 3 factorial, 5 factorial, 7 factorial, right? So this should be a factorial here and up here. So again, I'm using purple on purpose. That way you guys can see where it was changed. Okay, so the factorial. I forgot to put that down in our Maclaurin series. So now that I have that, let's start canceling stuff out. And I'm going to expand it since it's been Christmas break. Let's not go through it real quick. Let's show you the in-between step really fast. So this is x to the 2n times x to the third over. Now, between 2n plus 3 factorial and 2n plus 1 factorial, the 2n plus 3 is bigger. Okay? So, I'm going to expand that one. So there you go. I expanded it, and I stopped at 2n plus 1 factorial because that's when it matches. On the top, it's going to be a 2n plus 1 factorial, and on the bottom, it's x to the 2n times x. Are we okay so far? Any questions? Again, I'm just breaking it all apart. Let's cancel. I can get rid of 2n plus 1 here, x to the 2n there, and I can also get rid of 1x power here. So x squared will show up because that x over there will disappear. So let me write this out cleanly again. This is the limit as n approaches infinity of x squared over 2n plus 3 times 2n plus 2. But remember, the variable that matters is what? Is it x or n? N. So the x we kind of treat like a constant of sorts, right? So I'm going to factor it out. And I get the limit as n approaches infinity of 1 over 2n plus 3 times 2n plus 2. What's that limit? 0. So absolute value of x squared times 0 is equal to 0. Now, it's supposed to be set what? Less than 1. Well, since this is a true statement, what does that mean about my interval of convergence? It's everywhere. It's infinite, right? So my interval of convergence is from negative infinity to positive infinity. So here's one of my answers for this problem. Right now I'll go back down there. Just give me a second. And my other answer is right up here. So the Maclaurin series is there. And there's my interval of convergence right there. So this next example, I'm not going to ask you to find the interval of convergence. I'm just going to ask you to find the Maclaurin series for sine of x squared. Okay? But before I do that, any questions? Notice it's very important that you're good at doing the ratio test because you tend to use it anytime you got to check for convergence for a series. Okay? Or the root test might be helpful. Yeah.
Can you go over again? How did you know to use the x to 2n plus 1?
X to the 2n plus 1. Oh, at the very top?
Yeah.
Oh, it's because notice my powers had to be a 1, a 3, a 5, and a 7, right?
Yeah.
So since my powers have to be odd, then I have to use an expression that makes odd numbers. 2n plus 1 or minus 1, these are odds. 2n, these are even. So if you use a power of 2n, that means your powers will always be even. If you use a 2n plus 1 or a minus 1, they'll be odd. The way I need to pick plus 1 is if I plug in a 0 into, say, 2n plus 1. It becomes a positive 1, right? That means that my 0th term is an x to the first, which is exactly what I need. If I use 2n minus 1 and I plug in a 0, I get negative 1. And my power up there is not x to the negative 1 to begin with. It's x to the positive 1. So that's how I knew I got to use the positive one, not the negative one. And then again, the 2n plus or minus 1 depicts odd values. Odds only. So if it was going 1, 2, 3, 4, 5, 6, then just use n. Because that counts normal, 1, 2, 3, 4, 5, 6. But 2n will be evens, 2n plus 1s minus 1s will be odds. All right, so example 2, this one's going to be really quick, okay? Well, depending on whether or not you have this stuff memorized. But write the Maclaurin series and I guess you don't have to write the whole series, but just give me like 5 or 6 terms, let's say, okay? Maybe 4 through 6 terms. Write the Maclaurin series for f of x equal to sine of x squared. Now, remember, you guys should already know sine of x, so let's do that. Sine of x, centered at 0, looks like this. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus etc. If all they want you to do is change it to sine of x squared, then all you have to do is plug in an x squared where there originally is an x. So you're going to do this. Sine of x squared is x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7th over 7 factorial, etc. Okay, so now that you have that, just simplify x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial, etc. Now, we already know what sine of x is as a Maclaurin series, right? We wrote it up here. Right now, I'll go back down, but I just want to copy this really quick. So let me copy this piece here. So let's go back down. So we know that this is the Maclaurin series. But that was for sine of x. What do you think I do if they want sine of x squared? Just, yeah, instead of the x right there, you're going to have to square it. So let me write this in green here. So I'm going to write the sum as n goes from 0 to infinity of negative 1 to the n of x squared to the 2n plus 1 over 2n plus 1 factorial. You do have to simplify this, okay? So this will be the sum as n goes from 0 to infinity of negative 1 to the n of x to the 4n plus 2 over 2n plus 1 factorial. And this would be your Maclaurin series. Now, if you test it, you plug in a 0, you get x squared, right? If you plug in a 1, you'll get a negative x to the 6th over 3 factorial, which is good. That's exactly what I want. If you plug in a 2, you get a positive x to the 10th over 5 factorial, right? It's working. You don't have to try to figure out the weird pattern that it is because you already have the original pattern and you just manipulate it. Okay? So not too bad, right? I mean, as long as you have these things memorized, it should be pretty easy. All right? If you don't, then you got to go through the process of taking however many derivatives they want and plugging in your center and and that can take forever. Okay? So let me give you one more because we're going to skip this and all right. I'm going to give you this one. Now this one's a little challenging, but honestly, it's not terrible, but it looks really bad to start, okay? But you have to kind of pick what you know. So example number 3. Find the power series maybe not even we're just going to give the expanded portion of it, okay? A couple terms. Find the power series for f of x equal to sine squared of x. Now at first this looks like it's going to be super easy because you're like, oh well, I know sine of x, so sine of x squared is just sine of x times sine of x, right? Well, since the power series they're infinite, will you ever be able to finish multiplying your in other words, like look at this. If I were to ask you to do this and say, okay, now square it, are you ever going to finish? No, because this thing goes on forever. So that means sine squared x, even though it looks easy to do, we have to think of it in a different way. It's not just square your answer. Right? You're not just going to say, oh, it's this squared. Right? We can't do that. So how can we actually do this? Well, a long time ago, you guys might remember, I'm guessing maybe someone might remember this, but does anybody remember the power reduction identity for sine squared of x? So yes, trig still exists. It was 1 minus cosine 2x over 2. Now if you're saying, well, that doesn't look much easier, just give it a second. This is half minus cosine of 2x over 2. So check this out. If I know the power series for cosine, and then change its angle to twice, and then divide whatever I have by 2, and then make it negative, and then add half to it, I have sine squared of x. Okay, so let me go up there to kind of tell you what I was talking about. Okay, so what I'm basically saying is I should know the cosine definition. Okay, cosine of x. Right? That's an even function, so I know it starts with 1 and then minus x squared over 2 factorial plus x to the fourth over 4 factorial, etc. Then I just change it to 2x instead of cosine of x. Once I do that, I'll divide by 2. Whatever I have, I'll divide by 2. After I do that, I'll make it negative. So then I'll have this part complete, right? The negative cosine 2x over 2. And then the half will be added at the end. Okay? So we're going to do this in pieces. And then once we're done doing it in pieces, we're going to have sine squared of x, because that's the definition of sine squared of x. It's half minus cosine 2x over 2. So here we go. Start off with cosine of x. That's 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6th over 6 factorial plus etc. Okay, again, this is memorized. All right. Now, I'm going to change the angle to 2x. So cosine of 2x is 1 minus 2x squared over 2 factorial plus 2x to the fourth over 4 factorial minus 2x to the 6th over 6 factorial plus etc. Now I got to simplify that a little bit, so let's do that. It's 1 minus that's 4x squared over 2 factorial, okay, plus, now that's going to be, what is that, 16x to the fourth over 4 factorial minus 64x to the 6th over 6 factorial, etc. Are we okay so far? Just kind of small manipulation?
Why do we only do 3 or 4 of them?
Well, you can.
Set number that we have to go to?
No, in the AP exam, they'll tell you give us the 5th non-zero term. So in other words, write 5 terms. They might say like write 8 non-zero terms, so that means 8 terms. So I'm just doing 4 because I mean we can go on forever,
so, like,
but
they'll always tell us.
They'll let you know. Yeah, they'll let you know. So what I'm going to do now is I'm going to divide it by a -2. Okay? Notice I'm trying to piece this together right here. So I'm going to divide by a -2 right now. So negative cosine 2x over 2 is equal to. So if I divide by -2, I get a -half plus 4x squared over 2 times 2 factorial. I know I'm kind of making a little bit of a mess there, but we'll try to clean it up in a bit. Okay? Minus 16x to the fourth over 2 times, what is it, 3 factorial? No, 4 factorial, sorry. 4 factorial plus 64x to the 6th over 2 times 6 factorial plus etc. So let's clean it up just a little bit. That's -half plus 2x squared over 2 factorial. Notice I'm still leaving the factorial there, okay? Minus 8x to the fourth over 4 factorial plus 32x to the 6th over 6 factorial, etc. So to make this sine squared x, all I have to do is add a half to this. Okay? I just got to add a half. So I'm going to put half minus cosine of 2x over 2. Now remember, this is sine squared x. So if I add a half, what happens to that minus half there? It's going to go away, right? So this will be half minus half plus. Now let's simplify a little bit more here. This will just be x squared because the 2 divided by 2 factorial will go away. minus x to the fourth over, let's see, the 8, 4 times 2 cancels, so you have a 3, plus 32 over 6 factorial. What can I do? Let me do this. I'm going to erase this work right now, okay? But 6, 5, 4, 3, 2. So I can divide by 2. That'll make it 16. I can divide by 4. That'll make it a 4. And that's all I can do. So it'll be 4x to the 6th over 90. 4x to the 6th over 90. Now this cancels. So final step. Sine squared x is equal to x squared minus x to the 4th over 3 plus 4x to the 6th over 90.
What'd you do with the 1/2?
The half minus half will cancel away. They'll cancel out, I mean.
But you did 1/2 minus.
Oh, so yeah, so up here on this step right there, there was no half, right? So this is what it looked like.
Right.
Negative half plus 2x squared or 2 factorial, etc. On the next step, I just added a half to it. Because if I write this out, then I showed you guys up here that half minus cosine 2x over 2 is the same as sine squared x, right? So I'm just trying to piece it together, right? Put it together little by little. So once I get that half in there, then half minus half is 0. So then all I have is this. Now, just so you guys are aware, if they wanted you to write like a Maclaurin series for this, it's really hard to write a Maclaurin series given that. Okay? This thing, it's hard to write it with this. I would recommend leave it like this, put your half in the front, cancel it out, use this to write your Maclaurin series. Because at least there you can say like, okay, 2, 4, 6, my factorials are even, so it's 2n factorial. And then the top, you try to figure out, okay, 2 becomes 8, becomes 32. How can I get that? I notice my powers are even, so x to the 2n. So all you kind of have to figure out is just your 2, your 8, and your 32. Like, how do you get that? Okay? Whereas if you see it like in the answer that I put right here at the very bottom, that's kind of hard to figure out the trick for that one. It doesn't look like they have anything in common other than even powers and alternating plus and minus values. Okay. Oh, I forgot to put the plus stuff. So I'll put it right here. Okay, so I'll stop right there.